Hi there, welcome to another presentation on differential equations. My name is Charles Wells-Van. Our topic today is on separation of variables. How it's solving equations by means of separation of variables.
Let's look at the types of differential equations which we've so far looked at. Remember with exponential growth and decay, which was described in terms of this equation, first order differential equation, and the Newton's law of cooling was described by this type of equation. What is important, which I want to highlight here, is that to solve these equations, first of all, for the first one, we have to get to a point where we write y prime over y of t equals to k. And similarly, this side, before we could solve for y of t, we went through an equation of this form, where it's y prime of t over y of t minus the ambient temperature equals to k. Now this transformation actually leads us to a concept of what we call differential equations of separable variables. So let's say differential equations of separable variables. So we need to sort of engage ourselves with this concept of separable variables. First of all, in general, if we're given a differential equation of this form, let's say y prime equals to f of x y, we need to understand in this case here that y is actually a function of x, and y prime here will be then given as dy dx equals to f of x y. So then the issue is, when do we normally say an equation is of separable variables? Now, I would say that an equation, first order equation of this nature is of separable variables if this function of two variables here can be written in the form h of x over g of y, which, looking at it closely, this is same as saying this is equals to 1 over g of y multiplied by h of x. In other words, an equation of this nature is of several variables if we can actually write it as a product of two functions, one a function of y and a function of x. At the end of the day, you can see that this equation then would be y prime. Let's say y prime equals to h of x over g of y, which means that can be equivalently written as g of y prime equals to h of x. So if we look at this last expression here, it's like we've got expressions of y on one side and expressions of x on the other side. Then we say that the variables have been separated. So this is this is how we can identify that a first order differential equation given is of separable variables. I think what is important now is to look at examples and see how we can handle them. Actually, one comment we can make now before we look at an example is that these equations which we have looked at before are actually equations of separable variables. Now for example of this type of equation, let's say we're given y prime equals to 6x squared over y brackets 1 plus x squared. Now, transforming this equation, I think it is clear that we can actually reduce this equation to a product of two functions, one function of x and the other function of y. So to separate variables, in this case, I think it's easy. We can see that if we multiply by y on both sides here, we're going to have y prime here, and here we're going to have an expression of x only. So doing that, equivalent you've got here, y prime equals to 6x squared over 1 plus x cubed. Sorry, this is supposed to be cubed, x cubed. So now what we need to do now, if we're to solve this equation, remember we say this is dy dx, which means that we're actually searching for a function of x, which is the solution to the differential equation. So what we need to do now, we need to actually introduce integration on both sides, which in this case is going to be integral y prime dx equals to the integral of 6x squared over 1 plus x cubed dx. So integrating both sides in terms of x. So what we can appeal to now is we can appeal to our method of substitution. Let's say here let u be equals to y, dealing with the left hand side, and then our du dx is equal to y prime, which is equivalent to saying du is equals to y prime dx. So this side we're going to write u, and y prime dx is our du, going to have that as du there, equals to, on the right hand side we can do method of substitution similarly by declaring 1 plus x cubed to be our du. Then we write let u be equals to 1 plus x cubed. Now our du dx will be equals to 3x squared, which is equivalent to saying du is equals to 3x squared dx. So we've got this term here, 3x squared, hidden in 6x squared here, so which means we've got a 2 there which is redundant. We can filter it outside the integral sign. Then we write this as z2, and this, the 3x will be du, 3x squared will be du over u. So now we can integrate our expression now as u squared over 2 equals to 2 ln of u plus c. Right, here you have to be careful a bit. I used u for substitution on both sides, but we would have used the different variables. So, but then we have to be careful. What was u this side, and what is u for the other side? In this case, what we're going to do here, we're going to continue somewhere here. Let's say on the left hand side, our u was y, which means we've got here y squared over 2 equals 2. On this side, our u, we still have it there is 1 plus x cubed. Then we're going to have here ln of 1 plus x cubed plus c. So now I think we've finished solving our differential equation. The only thing we can now do is maybe to leave y as a subject formula and as an explicit function by first of all multiplying both sides by 2, then you get y squared equals to 2 ln of 1 plus x cubed plus c. And if you multiply c by 2 and the c is a real number, you still get a constant, so we'll leave that as still a c, and then therefore our solution is going to remain as y equals to the square root of 2 ln of 1 plus x cubed plus c. So this way we've gone through the whole process of solving our equation of separable variables. And as you can see, differential equations cannot be done or be solved without being very fluent in your integration and the differentiation. So you need to make sure that you practice that, which is actually part and parcel of this type of work. Now let's look at the second example. Now our example, as you know, we're dealing with equations of separable variables. We just need to look at the equation and see how we can separate variables and then proceed with our process of solving the differential equation. Now we've got dy dx equals 2 cosine x over sine y. So as you can see again, we look at the right hand side, which is our function. Recall that we said here this will be a function of xy. Now we need to try to reduce it to a product of two functions, each depending on one variable, one in terms of x and the other in terms of y. So what we have here is clear that we've got this equals to cosine of x multiplied by 1 over sine of y. So what you can do now, separate variables, you can multiply both sides by sine, which is going to give us a sine of y dy dx equals to cosine x. That is here multiplied by sine of y on both sides. Now at this stage here, we can do something similar by multiplying by dx on both sides. Then we get sine of y dy equals to cosine x dx. In this case here, we don't even need to do any method of substitution. You can just take this y as the independent variable of this function and differentiate goes to y, going to be integrated back to y, and this side we're going to in respect to x. So introducing integral sign on both sides, we get sine of y dy equals to integral of cosine x dx. So we know that sine as a derivative it comes when it's a derivative of cosine, but not necessarily sine, but minus sine. So to compensate for that minus, we can simply multiply here by minus 1 times minus 1 sine y dy equals to cosine x dx. What I've done here is a kind of a shortcut once we've used to our method of substitution. So because this one is an easy one, so what you can do now, we see this is a 1. So because we need this derivative to be minus sine in order to be a immediate derivative of function which we know. So we figure out 1 minus sine there is minus 1. Then we leave this as minus sine of y dy equals to integral. That is what is going to be there. So now, integrating the left-hand side, we can see that this is a derivative. Maybe this is put in brackets here. This is a derivative of cosine. Then that derivative is going to be multiplied by this constant minus 1. Then we get the left-hand side as minus cosine y equals to, and the cos we know is a derivative of sine, so this would be sine x plus a constant c. Now, what you can do, we can now multiply both sides by minus 1, and you get cos sine y equals to minus sine x plus c. We don't mind the writing plus c because we don't know really the sign of c. We can still continue with a plus c. Then, if you want, you can either leave the function like this implicitly, y implicitly, or since this case is possible, you can apply the second function cosine on both sides, then get y equals to cosine second function of minus sine x plus c. And we recall that the solutions like we saw in the previous example, which we leave with the c, we call them general solutions. Unless if we're given the initial conditions, we'll leave the function as a general solution. So I hope this is enough for this type of equation. Now I want to look at one or two examples with you where we find a particular solution, ours where we determine the value of this c, which we can only do when we're given the initial conditions. Okay. The order now is solve the following initial value problems. Now it just means that we're given initial conditions. So the problems are, we've got y prime equals to 4x squared over y, and we're given that y at 0 is equals to 2. On the line we've got y prime equals to 3x over 4y plus 1, and we're given that y at 0 is equals to 4. So I'll do one of the problems just to give an idea of how you normally determine the value of the constant c in the general solution. So maybe let's pick this one as a problem just want to solve together, then you can try the next one. So let's number them here 1 and this one 2. So given y prime equals to 3x over 4y plus 1. So now we see here that if you multiply both sides by the denominator, we're going to have one side expression one side expression of x and on the other expression of y. So multiplied by 4y plus 1, we get here 4y plus 1 y prime equals to 3x. Now, once we've done that now, we introduce integration on both sides. Then we have this as integral of 4y plus 1 y prime dx equals to integral 3x dx. So on one side, this side, I think you can see that we need our methods of substitution. Then we let our u be equals to 4y plus 1. Then our du dx is equals to 4y prime. And one differential derivative is equal to 0, which this is equivalent to saying our du is equals to 4y prime dx. So what we're going to have here now, we note that here on the problem we've got y prime dx, which is y prime dx, so we need to substitute that. Then we're going to have here du divided by 4 equals to y prime dx. So now substituting here, we've got u multiplied by du over 4 equals to 3 integral of x dx. Now here we can filter 1/4 outside the integral sign, so then integrate u using our power rule. Then we leave this as 1 over 4 multiplied by u power 2 over 2 equals to 3 multiplied by x squared over 2 plus c. So now what you can do now is to simplify this, and we can multiply both sides here by 8. So you see that the denominator is going to be 8. Then we're left with u squared equals to, multiplying by 8 here, we're going to have 4 times 3, which is going to be 4x squared, and the 8 by constant is going to be a constant. So now our integration is stopped there. What we need to do now, you need to substitute backwards and make sure that we leave our function in terms of y and x. So we've got here 4y plus 1, 4 plus 1 squared equals to 4x squared plus c, which we can simplify also by finding the square root on both. We get 4y plus 1 equals to square root of 4x squared plus c. Now to make y substitute the formula, we can see that we need to subtract on both sides 1, and then that's divide by 4, which is going to give us y equals to square root of 4x squared plus c minus 1 all divided by 4. And at this stage here, we have obtained our solution, in this case, which is our general solution. So I'm just going to write the gx for general solution. But now, because we're given the value, the initial value that y is 0 is equal to 4, we need to use that in this expression so that we can now give what we call a particular solution. So we need some space here. Let's open up here. Our general solution is y equals to square root of 4x squared plus c minus 1 all over 4. Recall that when we say y at 0 is equal to 4, we actually mean that the function we're obtaining here passes through the point 0, 4, which means our x coordinate is 0 and the y is equal to 4. So substituting that here, we get 4 equals to square root of 4 multiplied by 0 squared plus c. You can see what I'm doing here. I'm just mimicking the expression function under the square root sign there. Minus 1 all over 4. So what we get here is that 4 times 0 is 0 plus c minus 1, we're going to get square root of c minus 1 divided by 4 equals to 4. Simplifying this, we're going to get 16 multiplied by 4, multiplying all this by 4, that's 16 equals to square root of c minus 1, which gives us square root of c equals to 17. If our calculations are correct, then we get that c, therefore c is going to be equals to 17 squared. If everything is correct, c must be equals to 17 squared, because we square both sides here to get c, then we get that as 17 squared. So now finally our particular solution would be y, you can write it as a function, y, a function of x equals to square root of 4x squared plus 17 squared all over squared minus 1 all over 4. I trust that is correct, but please try to check the number work and see whether we got exactly what you wanted to get. Otherwise, this is how we would handle the situation where we are required to find a particular solution because you are given initial conditions. I hope this gives you a good kickstart.
Otherwise, at this point, I would like to say thank you for listening.